Composition of compounds. So chemical formulas tell us about the composition of compounds. They tell us the number of atoms, right, of each different type of element. I lost my train of thought. When we're looking at the molar masses along with that chemical formula, then we can look at relative masses of the different elements. And one way to do this is what's called a mass percent composition, or just a mass percent, or sometimes we call it the percent composition of an element in a compound. And so it's very helpful to understand the basic formula for percentages. A percent is the part that you're interested in divided by the whole thing times 100. Okay? Here I've given percent as if it were a unit. In the worksheet, it did not have percent there. No matter what I do, a group of students will misinterpret what I've written. So what I saw happening when I didn't write percent here is that students would calculate that, part over the whole times 100, and then they'd multiply by 100 again to make it a percentage. So that's not right. And when I put it this way, students do part over the whole, and then they either use the percent button on their calculator, which gives them a 1 here, or they say, well, times 100%, that's times 1, and then they don't multiply by 100. So don't use the percent button on your calculator ever in this class. Do not. I don't even know where mine is because I never ever use it. Don't use it. Yeah, no, don't. Okay. No. We don't want to know where it is. Don't use it. Okay, so I'm using percent as a unit. So part over whole times 100, okay?
So you would get an equation when you put times 100%?
Well, times 100%, I'm using percent as a unit. So it's not that we're saying 100% of something. It's in this equation. And I realize I somehow skipped this for the Monday, Wednesday class. I was wondering what happened. So here's the formula for finding the mass percent of an element in a compound. The percent of X, whatever element you're interested in, is the mass of X in 1 mole of the compound divided by the mass of 1 mole of the compound times 100. If you don't multiply by 100, then you get the fractional composition, which if it's asking you for percent composition, it's not going to be correct. So we can get it from the formula of a compound. We can also get it from experimental mass analysis of a compound. Say you took 5 grams of this substance and you decomposed it and you collected one of the elements and weighed it, and you've got the mass of that element. You just take the mass of the element divided by the mass of the compound it came from times 100. If you do this for each element in the compound, in theory, they should all add up to 100%. In practice, it doesn't always come out to be exactly 100%, because if you're doing it from the formula of the compound, there could be rounding issues with how you rounded your results. With an experimental value, there could be uncertainty issues with your masses. Okay, so if you add them all up, they should come out very close to 100. So let's calculate the mass percent composition of oxygen in acetic acid. Acetic acid is the active ingredient in vinegar. Do we need to know that? Not necessarily, no. Mass percent composition of oxygen. So we're given this formula. There are no numbers in this problem. That can be a bit disconcerting. How can I do a calculation without any numbers? Well, we're going to get our numbers off the periodic table. The thing about a percent composition, the percent composition is the same if you have a teaspoon of it or a gallon of it. the percent composition is the same. So the actual amount of substance that we're looking at doesn't matter. So we have to just choose an amount. We've got this formula, so we can calculate. So what's easiest is to choose a mole. We said, well, I'm going to do this calculation for 1 mole of acetic acid. That makes the calculations easier. So we're just going to choose 1 mole. So we're looking for oxygen. The percent of oxygen is equal to the grams of oxygen divided by the grams of the whole thing times 100.
So the units are always going to use grams in every percent of...
No, the units are actually going to be percent.
No, I mean to calculate the percent, to get the number.
Well, you need to use a mass unit. You could use kilograms. You could even use pounds, except we wouldn't do that because we're chemists.
You don't always have to use 1 mole?
You don't have to use 1 mole, but it's going to be more difficult. You know, if you want to do 5.5 moles, go for it, but it's going to be more work, right? So by choosing 1 mole, I'm going to ask myself, well, what's the mass in grams of 1 mole of this? Well, that's the molar mass, right? Yeah, I have to calculate it, but I can do that. So 2 times the mass of carbon plus 4 times the mass of hydrogen, and 2 times the mass of oxygen. Thank you for that, but I can't listen to you when I'm punching buttons. Yeah, 60.052. So confirmation, that's always good. So that is the molar mass of acetic acid. The way I did it, it have 4 cities. So 1 mole of acetic acid weighs that much. Okay, so that's going to be the denominator in this equation I've got here. Grams of acetic acid would be 60.052 grams, because I chose 1 mole. What is the mass of oxygen in that 1 mole? Oops. I don't know what happened. That used to just scare me because I didn't know how to get it back. Now I know which button to push. Well, how much oxygen is in this compound? There's 2 oxygen atoms. Right here is the mass of oxygen. You write this out, and you've actually done some of the work for finding the mass of the element. So 2 times oxygen, so 32.00 grams of oxygen in 1 mole of acetic acid. That's why choosing 1 mole just makes it so much easier. Otherwise, you'd have to multiply both of these by whatever number of moles you picked. So we'll put 32.00 up here. Bless you. And then times 100%. Now what happens to these units, gram and gram? They cancel out. In a percentage, they should always cancel out. Grams cancel. 32.00 divided by 60.052 times 100. 53.28. 53.28. There's my 4 sig figs. And then 7.1%. So 53.29% oxygen. By mass, acetic acid is 53.29% oxygen. You wouldn't guess that looking at the formula. There's 2 atoms of oxygen in a molecule. There's 2 atoms of carbon. There's 4 atoms of hydrogen. But each of them has a different mass. Hydrogen weighs a lot less than oxygen, and that's why oxygen by mass is a larger percent. Questions? Mass percent can be used as a conversion factor. So percent actually means per 100. So we can say, well, the percent is the part over the whole times 100, or we can say it's the parts of what we're interested per 100 parts total. So Freon 112, this is its chemical formula. 69.58% chlorine by mass. So we can take that and say, well, that means 69.58 grams of chlorine per 100 grams of Freon 112. That's what percent means. Right? So if 75% of the dentists prefer this certain gum or whatever, 75%, that means 75 out of 100 dentists prefer this thing, right? We use percentages in our everyday lives. And sometimes we just, we've gotten so used to them, we don't think about what they actually are. If you understand what percentages are, it can make your life simpler. Like, looking at shoe sales or something and figure stuff out. So we'll do a problem using mass percent composition as a conversion factor. What mass in grams of iron 3 oxide contains 58.7 grams of iron. Iron 3 oxide is 69.94% iron by mass. So we've got two numbers here. So I'm just going to follow the sort of pattern I've been using. So we read the problem. Now we're going to write down the numbers. 58.7 grams of iron, Fe. And then we've got this percentage, right? 69.94% iron. Percent means per 100. So that is the same as 69.94 grams of iron per 100 grams of the compound, iron 2 oxide. Yes?
It's iron oxide, not just iron, right?
Right. It's iron 3 oxide. So this is, it's 69.94% iron for every 100 grams of iron oxide. So down here, we don't just put iron, we put iron 3 oxide. So that formula would be Fe2O3. Would you have to know that for this problem? No, you wouldn't. You could write compound there. And then what are we trying to find?
Wouldn't you use it as a conversion factor?
We're using it as a conversion factor, yeah, definitely. We're trying to find the grams of the iron oxide. I'm using the formula because it's a lot quicker to write than iron 3 oxide. So I have grams of iron, I want grams of iron 3 oxide. This is the conversion factor. The percent composition tells me the relative masses of iron and the entire compound. So this is going to be one step. 58.7 grams of iron. I'm going to have grams of iron oxide on top because that's what I'm wanting to figure out. And I'm going to have grams of iron on the bottom. I put the units in first, and I use horizontal lines in my fractions so that I can clearly see what's in the numerator, what's in the denominator. So there's my units worked out. Now I look at this percentage that I wrote out. 100 is with the iron oxide, so that goes on top. And the 69.94 goes with grams of iron. I don't have to think about, was I supposed to multiply or divide by that? What do I do? The units tell me what to do. Units are your friends. You may have to make friends with them, but they will treat you well if you treat them well. So this comes out to 83. We should have 3 sig figs here, 83.9, and then 2.9. And then we'd round that to 83.9 grams of the iron oxide. For sig figs in this percentage, Percent by definition is per 100. So this 100 is an exact number. The 69.94 is not exact. That has 4 sig figs. This had 3, so I rounded this to 3. Any questions? We can also get conversion factors from the chemical formulas themselves, because the formulas tell us how many atoms of each element or how many moles are in a molecule. So for this Freon compound, C2Cl4F2, 2 of these several possible conversion factors are that there are 2 moles of carbon in 1 mole of the compound. Because in this molecule, there are 2 atoms of carbon. So we're just scaling up by making it moles. There are 4 moles of chlorine to 1 mole of Freon. It's just from this formula. And we could also say there's 2 moles of fluorine per 1 mole of C2Cl4F2. Okay? The chemical formulas gives relationships in moles, not masses in grams. So let's see how we would use this. Determine the mass of oxygen in a 7.2 gram sample of aluminum sulfate. So we write down the number, 7.2 grams. So we got 7.2 grams of aluminum sulfate. We're probably going to need the formula for that. We've got Al3 plus and SO4 2 minus. So we're going to get Al2, SO4 3. Yeah, that's a mess. And what do we want to find? Mass of oxygen. So grams of oxygen. If they told us the percent oxygen in aluminum sulfate, we could do this in 1 step. But they didn't tell us that. We could calculate the mass percent of oxygen in aluminum sulfate and use that. But that's not actually going to be any faster than just going through moles in the middle. So we can go from grams of aluminum sulfate to moles of aluminum sulfate because we can calculate the molar mass. So we can go to moles. Al2SO4. And if we had moles of oxygen, we could get grams of oxygen. This moles in the middle part, so looking at the formula, we get this relationship. There are 12 oxygen atoms in 1 unit of this compound. So if we have a dozen, we would have 12 dozen oxygen atoms. If we have a mole of the compound, we have 12 moles of the oxygen. Okay? This factor comes directly from the subscripts in the formula. And yes, it's very tedious writing that formula out over and over again. But doing the problem over and over again because you screwed up is, that gets a little tedious too. What am I doing? I'm writing with an eraser. Doesn't work very well. Nope, that's a 3. Got to copy those things down. Okay. And I'm going to have grams on the bottom. And then I need to go to moles of oxygen. And, oops, moles of oxygen. I'm going to have moles of that guy. Al2SO43 on the bottom. And then I'm going to convert to grams of oxygen per mole. Okay, so these moles cancel. So any questions about that?
Would it be 12 oxygens for 1?
Mm-hmm. Yep, this mole ratio here is 12 moles of oxygen to 1 mole of aluminum sulfate. Because in this formula, in one of these units, we have 3 times 4, we have 12 oxygens. If you were doing sulfur, how many sulfurs per mole? 3. And aluminum? 2. There's 2 aluminums in 1 unit. So there's 2 moles of aluminum per mole of the compound. We only need the oxygen one. Then I always like to do the easier ones first. Oxygen molar mass is very easy. So that's 16 grams of oxygen is equal to 1 mole of oxygen. And then you got this guy. Okay, 2 times 26.98 plus 3 times sulfur plus 12.
You just know these?
I do just know these because I've used them so much. I never sat down to memorize these, but if you do them over and over again, after a while, you just remember that, yeah, aluminum's 26.98.
She has a cheat sheet. It's on the
342 point.
Yeah, it's on the
Like after a while you get used to it.
So you got 342.17
Well,
or close to that.
Yeah, 15.
So with my numbers, 342.17. And that's why I do the 4 sig figs, is because they're in my head. It just makes things so much faster. So that's grams per mole for aluminum sulfate. So that's the number I need over here. 1 mole of it weighs 342.17 grams. I think it's best to keep those extra digits along just to avoid rounding errors. So now we've got 7.2 divided by 342.17 times 12 times 16. We should end up with 4 significant figures. No, 2, I'm sorry. The number is 4, 2 significant figures. So you're getting 4.0399. I'm getting 4.04.
009.
Whoops. Yeah, 00, and then it's 97, etc. So when we round this, we're both going to end up with the same number, 4.0 grams of grams of oxygen, sorry. Any questions? When I do the molar mass of oxygen here, I am not thinking of oxygen as a diatomic element. Oxygen is a diatomic element when it is by itself, because oxygen atoms do not like to be alone, okay, junior high girls. But the oxygen atoms are not alone. They're on this group date with sulfur and aluminum, right? They're all just going out, hanging out together, going to a movie. So they're fine. So we can look at them as individuals there.